Hi, more simple harmonic motion. Today, let's talk about spring mass systems. Start with a horizontal spring attached to a mass M. Assume the spring has no mass or friction and that it obeys Hooke's law. Hooke's law says the spring force is proportional to X, the stretch in the spring. The constant of proportionality is K, the stiffness coefficient. Units for K are force per length, usually Newton per meter. When the deflection is positive, the spring pulls back. The force is negative. When the deflection is negative, the force pushes forward. It's positive. The spring force is always directed back to the unstretched position. It's called a restoring force. Okay, physicists, we have a force. We are analyzing motion. What do I want you to do first? Tick, 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 tick. I know you're all thinking it. Make an FBD. It's a boring FBD. There's only one force, the spring force. The net force acting on the mass is negative kx. This body is not in equilibrium. Its motion changes constantly. Time for Newton's second law. The net force acting on a body equals the mass of the body multiplied by its acceleration. Net force, negative kx, equals ma. Divide both sides by m and we get the acceleration. It's proportional to the deflection. Wait, does this equation, this differential equation, look familiar? Remember the simple pendulum? For a pendulum, alpha, the angular acceleration, equals negative g over L times the angular displacement, theta. Holy moly! Both equations say the acceleration is proportional to the opposite of the displacement. From pendulums, we know the motion can be described by sines and cosines. Simple harmonic motion. I know. You're thinking, this is a vertical spring, not a horizontal one. Do they act the same? That's a fair question. Do horizontal and vertical springs act the same? Let's take a look at a vertical spring. The unstretched and equilibrium positions are no longer the same. Now, let X represent the location of the mass with respect to the equilibrium position, not the unstretched position. The stretch in the spring is the sum of D, the equilibrium stretch, and X. Let's FBD the mass. The spring force pulls up, the weight force down. Define down as positive. Apply Newton's second law. The net force equals ma. Net force, that's mg down, so positive, minus the spring force up, k times d plus x. This net force equals ma. Distribute the k and rearrange. mg minus kd. mg minus kd? Hold on. If it walks like a duck and it quacks like a duck, well then, it's probably a duck. In this case, we're talking equilibrium. D is the equilibrium stretch. In equilibrium, the force up, Kd, equals the force down, mg. So, quack, 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 mg minus kd must be 0. Solving, we get the acceleration a is the opposite of k over m times x. Yes, you are seeing that right. The exact same formula that we found for horizontal springs. Define x as the displacement from equilibrium, and we have the same behavior for horizontal and hanging springs. The motion can be described as a sine or cosine function, oscillating back and forth across the equilibrium position. Special note, for horizontal springs, x is the stretch. For hanging springs, the stretch is x plus d. According to theory, the period of a spring mass system is proportional to the square root of m over k. What happened in your lab? Did the period depend on m to the 0.5 power? Did the period depend on k to the negative 0.5 power? And your constant, was it 2 pi? I know that you are all nodding. Yes, yes, and yes. This may sound like a funny question, but what don't you see in the equation? Think back to your lab. G isn't there. Amplitude isn't there. What about units? Let's do a units check. We have 2 pi radians per cycle. That's an invisible unit. Mass has units of kilograms. K, the stiffness coefficient, has units of newtons per meter. 1 over 1 over. Move the meter upstairs. Remember, F equals ma. A newton is a kilogram times a meter per second squared. Cancel the kilogram meter on top and bottom. Simplify, and we end up with seconds, a very appropriate unit for period. Does the formula make sense? If you increase its mass, that's inertia. Wouldn't it be harder to change the motion of the block? Wouldn't that slow everything down? That's what the formula tells us. Bigger mass, bigger period. And what if spring stiffness was increased? That's what makes the mass move back toward equilibrium. K is downstairs. Bigger K, smaller period. There's another quantity used to characterize simple harmonic motion. Yes, frequency. The units are, no, I won't, I can't help it. Ouch! That hurts. Yes, the unit is hertz. Cycles per second. Period is seconds per cycle, so flip it and you get frequency. That's all for now, folks. See you soon.